Hello again, everyone. Mr. Cruze here with another trigonometry review for you. This time, the Chapter 4 trigonometry review, the Chapter 4 test review. Remember, the stuff that's going to be on this test is angular and linear velocity, which we'll cover in this video, graphs of inverse circular functions, which we'll cover in this video, exact values of inverse circular functions, which we covered in the last video, and a few story problems with inverse functions. All right. Let's dive right into these graphs. So the instructions on this say graph following on another sheet of paper. Here's my other sheet of paper. Be sure to list critical points for each graph. So we have y equals 2 pi plus the inverse cosine of 3x. All right. I'm going to start with the whole inverse cosine. And once again, this could be written one of two ways. They could write inverse cosine or they could write arc cosine. Same diff. There are three critical values for inverse cosine that we need to really know. Okay, they all involve negative 1, 0, 1. Every one of these arc functions all involve negative 1, 0, 1 in some way. Okay, we just have to figure out where is it what, right? Well, I know cosine is 1 at 0, and I know cosine is 0 at pi over 2, and it's negative 1 at pi. Alright, so there's my 3 points. Again, you can get those from the table if you're careful. So, now we just need to figure out what's going on in this particular problem. Well, anything that's inside the arc cosine is going to affect the x coordinates. Remember, these are our x and our y's, right? And unfortunately, it does the opposite of what we want it to do. So this says 3 times x. So the temptation is to think, oh, multiply all my x's by 3. But just like any good x, it has to do the opposite of what it says. So this is actually, you're going to divide all x's by 3. Okay. This part on the outside tells you what to do with y, and it's as written. The y's are cool. So this tells you to add 2 pi to all y. So what I do is I take care of x's first just to get it out of the way, right? Change color. So I'm going to divide all my x's by 3. So negative 1 divided by 3 is negative 1/3. 0 divided by 3 is still 0, so that's nice. 1 divided by 3 is 1/3. Okay, and again, you might be able to recognize a pattern. Then, there's nothing else we do with the x's, so they're all cool. All the y's, we're just going to add 2 pi. So pi becomes 3 pi. Pi over 2 becomes 5 pi over 2. And if you don't believe me, you can check. 2 pi is 4 pi over 2, plus pi over 2 would be 5 pi over 2. And 0 plus pi, or 2 pi, rather, is 2 pi. Okay, and again, you can notice a pattern. 3 pi, this is 2.5 pi, that's 2 pi. Alright. Once you've got your 3 points, all you have to do is sketch a graph. Doesn't even have to be pretty. I'm going to put negative 1/3 over here. I'm going to put 1/3 over here. We're going up, so let's see, pi, I'm going to do 2 pi, and we'll do 3 pi. So I know at negative 1/3 it's at 3 pi, so it's up here at 3 pi. At 0 it's at 2.5 pi, so we'll put it there. And then at 1/3 it's at 2 pi, and then I just graph it. And really the shape, I'm not so concerned about the shape. I should be, but I'm not. Essentially what happens is it starts off steep and then gets flat around the middle point and then gets steep again, okay? So as long as you have something that looks like that, everything should be good. Just make sure it has 2 endpoints. There's nothing beyond those, okay? If I were to try and go beyond those, it would not be a function anymore, okay? We're just limiting it to what it is. Alright? So there's that one. That's not so bad. 18, y equals 3, arc cotangent of x plus 4. Arc cotangent. Cotangent's a fun one because you actually have 5 things to deal with. 2 of them are asymptotes, though, right? Cotangent has an asymptote at 0. Okay, and once again, it involves negative 0 and 1. And it's got another asymptote at pi. Alright, and everything kind of fills in between those two. Actually, just to make sense of this, I should probably flip these. We'll do pi up here, and we'll do 0. Because at negative 1, the arc cotangent is 3 pi over 4. Then it goes down just by pi over 4. So this one would be pi over 2. This one will be pi over 4. And then we're good to go. Alright. So I need to figure out what is happening with the particular problem. Well, this is x plus 4. So I would think add 4 to x, but it's actually subtract 4 from x. And that's it for the x's. Out here we have 3 times, so that's multiply y by 3. Alright, so here we go. Let's subtract 4 from all our x's. Undefined minus 4 is undefined still. -1 minus 4 is -5. 0 minus 4 is -4, and you might be able to pick up a pattern here. Once again, undefined minus 4 is still undefined, still a horizontal asymptote. Multiply all y's by 3, well that's not so bad. Pi times 3 is 3 pi. 3 pi over 4 times 3 is 9 pi over 4, or 2 1/4 pi if you'd rather. Pi over 2 times 3 is 3 pi over 2. Pi over 4 times 3 is 3 pi over 4, and 0 times 3 is still 0. So let's sketch this graph. Actually, I don't really need a whole lot of the positive side. Let's go over here. 1, 2, 3, 4, 5. This will be -5. This is -3. This is -4, really. Let's see. I need to go up to 3 pi. So let's see. This can be pi. This can be 2 pi. Well, 3 pi. So you'll notice there is an asymptote at 3 pi, horizontal asymptote. There's also one at 0, and try and make this one stand out. If you need to, because it's on an axis, you can use a squiggly line, that way we see what it is. And then graph the other points. So -5 is at 2 1/4 pi, so we'll call it here roughly. -4 is at 1 1/2 pi. -3 is at 3/4 pi, so we're there. And then you just have to remember what cotangent arc cotangent kind of looks like. It just kind of loops through those points. Obviously, make sure you go through those points. And please attach arrows to the beginning and end of those. It does go on, the domain is all real numbers, so it does go on forever there. Alright. 19, y equals pi plus 3 arc sine of 2 times x minus 1. This one probably has the most going on in the problem. Alright. First thing I notice is it's arc sine, so I know that my points are -1, -pi over 2, 0, 0, and 1 positive pi over 2. So let's figure out what's going on here. Here we have a 2 times x minus 1. This tells me I'm going to divide by 2 and add 1 to all x. Okay, we might as well go ahead and take care of that. So, -1 divided by 2 is -1/2. Plus 1 becomes positive 1/2. 0 divided by 2 is 0, plus 1 is 1. And if I had a 10-penny nickel, I'll bet the next one's going to be 1 1/2. 1 divided by 2 is 1/2, plus 1 is indeed 1 1/2, or 3/2. Okay, again, you can notice a pattern as we go along. This part here tells me to do exactly what I see, so I'm going to multiply by 3 and add pi to all y's. So this gets a little fun because you end up with some fractions, right? -pi over 2 times 3 is -3 pi over 2. I'm going to write this out here. And then I'm going to add pi to it, which is actually 2 pi over 2, right? So this one comes out to be the same. This is kind of cool. -pi over 2. Alright. 0 times 3 is easy. That's 0 plus pi is indeed pi. And you could probably figure out the next one is going to be, well, you added 3 pi over 2, so that'll be 5 pi over 2. And if you're careful, you'll notice that pi over 2 times 3 is 3 pi over 2, plus pi is 5 pi over 2. Alright? Now let's graph it. And again, I don't know what's happening there. Again, you're just marking these off. 1/2, 1, 3/2, right? In the interest of time, I went ahead and skipped ahead. Yay, magic of technology. I just put -pi. I went by pi's along the axis there. So at 1/2 it's -pi over 2, so that'll be down here pretty much right where I wrote 1/2. That'll be right there. 1 it's at pi, and at 1 1/2 it's at 5/2 pi or 2 1/2 pi. Alright? And again, start off steep, approach kind of a flatter piece around the middle, and then go up. And there you go. Again, endpoints, so don't go beyond them. Easy peasy. Last graph, and then we'll get to the angular and linear velocity. Y equals 2 arcsecant x. Not a whole lot going on here. Arcsecant goes along with arc cosine, right? So we have several points. Once again, -1 pi, 0 pi over 2, and 1, 0. Okay? The only difference here is, instead of 0 for arcsecant, it's undefined. Okay? Other than that, it's the exact same. So we have a horizontal asymptote. Only thing happening here is we have a 2 times. So all you're going to do is multiply by 2 to y's. All your x's stay exactly the same. Your y's just get multiplied by 2. So pi becomes 2 pi. Pi over 2 becomes pi, and 0 stays 0. So let's graph this guy. So we have -1, and we have 1. Okay, we have a horizontal asymptote at pi. So I'm going to draw that in. And we go up to 2 pi. So at 1, it's 0. And at -1, it's at 2 pi. And then you ask yourself, well, how do I curve this? Well, you want to go towards the asymptote, but you don't want to cross each other. You want it to pass the vertical line test. So make sure you go opposite directions. The one on the left goes towards the left, the one on the right goes towards the right, and you just graph them. All right. Hopefully that was easy enough. Let's get back to the actual worksheet. Stan and his brother Ben played on a seesaw. Sam sits at a point 8 feet from the pivot. Ben, being heavier, sits just 5 feet above the pivot. So I'm going to draw a little picture here. There's the pivot. Let's see. Sam's at 8 feet away. Ben is 5 feet away. Okay. As Ben goes down and Stan goes up, the seesaw rotates through an angle of 37 degrees in 0.7 seconds. So 37 degrees in 0.7 seconds, that sounds like an angular velocity to me. What's Ben's angular velocity in radians per second? Well, I hope you would agree with me. Since they're on the same seesaw, the same rotating object, they have the same angular velocity. All right. So that's 37 degrees in 0.7 seconds. But we want it in radians per second. So I'm going to multiply by pi radians in 180 degrees. You could use 2 pi and 360 if you wanted to. So the degrees cancel, and I'm left with radians per second. So all you have to do is multiply 37 times pi. So 37 pi divided by 0.7 times 180. And make sure you use parentheses on this. And you should get, and I'm just going to leave it in decimal format just for quickness sake, 0.99 or 9225 radians per second. So that is your answer for number 21, 0.9225 radians per second. What's Ben's linear velocity in feet per second? Well, to go from angular velocity to linear velocity, don't you just multiply by the radius? So this shouldn't be too bad. What is Ben's radius? Well, Ben is 5 feet away, so you're going to multiply by 5 feet times the 0.9225 radians per 1 second. And again, the radians really aren't a unit, so that'll give you feet per second. So just multiply by 5, and you should get 4.613 feet per second. So 4.613 feet per second. All right, what's Stan's angular velocity in revolutions per second? Revolutions per second. Well, again, remember, they're on the same rotating object, so they have the same angular velocity. So it's still the same 37 degrees in 0.7 seconds, right? And you can go ahead and change this to revolutions per second, right? How many degrees are in 1 revolution? Well, that's 360 degrees, right? You could, by the way, change the radians one if you wanted to. It's not a big deal. It'll come out the same. So anyway, basically take 37 divided by 0.7 times 360, and you should get a final answer of 0.1468 revolutions per second. All right. And last but not least, what's Stan's linear velocity? Well, again, take his angular velocity, which is the same, by the way, as Ben's, 0.9225 radians per 1 second. I'm using radians per second because that's technically his angular velocity. Only multiply by his radius, which in this case is 8 feet. All right. And when I multiply those two together, I get feet per second, which is what I want. Make sure you're in the correct units that they want. 7.38 feet per second. Okay. Once again, make sure you're watching units. If they wanted inches per second, just change feet to inches, right? And then the last but not least is make sure that you know how to work problems from section 8. Okay, I'd work on the odds. Well, that's it for this video. Whew, we're almost out of time. Almost reached the 15-minute mark. If you have any questions, please make sure you come in for help, all right? Good luck studying. I will see you tomorrow.